I've got an efficiency story to share with you. And I mean, it's fun from my perspective, but then again, I have a perspective of a parent. Maybe if you're a parent, you'll also get it. Okay, so my son was about 2 years old. Maybe he was 2 to 3 years old. And he was playing on the dining room table. This was one of those days where I was super tired. I didn't want to have anything to do with anything. So I was laying down on the couch beside the table. And so he decided he wanted to go play with marbles. There happened to be a bowl of marbles on the table, but he wanted to take those marbles and take them elsewhere, put them on the floor. So the bowl of marbles, probably about 20, 30 marbles in there. And he went and picked up the bowl of marbles. And of course, he's being very careful, right? It is a bowl of marbles after all. And he slowly gets off his precarious perch on the chair down to the floor. He does it successfully. And he starts walking to an area of the floor that he wants to play with. I'm lying down on the couch watching this and envisioning what's about to happen next. He's so focused on the bowl of marbles that he forgets to pay attention to the fact that his feet are going in front of one another. Oh, he took a tumble. He took a tumble, and it wasn't so bad for him, but the marbles, they were everywhere. We had marbles going underneath couches, behind carpets. They were going into places never to be discovered again. They were going into those little air holes where you have the vents to do the air ventilation in the house. They went everywhere. And I remember the first thought I had was, oh, gosh, I gotta get up now and clean this up. He was unfazed. He decided to take the inefficient approach. He took his bowl and righted it, put it on the floor, walked over to the next first marble he could find, pick it up, walk over back to the bowl, put it in. And then he chased down another marble, picked that one up, and went back and put it in. And I'm watching him do this. I'm like, why? You're going to do this one by one? This is going to take forever. And then it hit me. Wait a minute. If this takes forever, that is that much time that I have to sit back on the couch and relax in peace and quiet. If you're a parent, you know how fleeting those moments are. So I enjoyed it thoroughly. Oh, that was good. He finished his task, and I was rested by then. But normally, we don't want to do things one by one, right? We want to try to scale things up and become a little bit more efficient, like the circuit that we have right now. We have a single LED that's being driven by this circuit, very well might I add. But if we wanted to add more LEDs, does that mean we have to take our circuit and, double it, triple it, do it 50 times, 100 times to fill a room? Because, by the way, that's what we're trying to do, right? We're trying to illuminate a room, and you can't do that with one LED, no matter how powerful it is. Well, maybe you can, but not with the power that we want to try to push. So we want to try to scale this up. And we could, add more circuits, but I think there's a better way to do it. We can probably add more LEDs into our existing circuit. Well, there's a few ways we can do that. Let me bring up the circuit diagram here, and we can look at it. So here's our circuit that we have right now. And if we look at the circuit, here's our LED right over here. We can add more LEDs in a couple of different ways. Here's one way we can add some more LEDs. If we do this, what we're doing is we're adding LEDs in parallel. So we're stringing them together. And this will work. It'll work. We'll get all the LEDs connected and they will all light up. But there are two reasons we may not want to do this. One of those reasons is, if you remember the way current works, when current finds multiple paths to go through, it wants to go through all available paths, but it will split itself up and divide itself so that it can go through all those paths. So what that means is, if we have current coming in and going through all these LEDs, since the current is splitting up amongst the LEDs, they're all going to be illuminating a little bit less bright. In fact, if we have this many, then it's going to be really dim, frankly, right? We're taking the current that was designed based on this circuit for one LED and splitting it among 6. Well, we could fix that if we simply change the rest of the circuitry to try to pull more current so that it gets divided out better. But that brings us to the second reason this won't work. LEDs are manufactured not really exactly the same. So if I have a handful of 6 LEDs, it's rare to find exactly the same LEDs. And that means that if I wire it up this way, because of the slight differences in these LEDs, One is going to be slightly more illuminated than the other. It's going to be subtle, but the effect is going to be there, and you're going to be able to see it. And we don't want that. So this may not be the best way to do it. There is another way. We can wire these LEDs up in series instead of doing it in parallel. And what that means is we do them one after another, just like that. We do it like this, then the current that was going through one LED is the same current going through all the LEDs, because the current has only one path to go through here. And that means that all the LEDs are going to have the same brightness. This is far better. The downside of this, though, is the amount of energy that we have to push into this circuit. If you remember from a previous video that I did, I was talking about how when you provide energy to an LED, it's almost like that energy encounters a wall. And it's got to get over that wall in order for that LED to light. And if the supply voltage, the amount of energy that we're giving our system isn't efficient or isn't sufficient to get over that wall, then the LED is not going to light. And so far, we've been giving our circuit 5 volts. And if you remember, a white LED drops somewhere between 2.8 to 3.6 volts. Well, that's below 5, which means that we have enough energy to light up the LED and continue along its path. But if we add just one more LED to this, and let's assume that both of these LEDs are best case, they drop 2.8 volts. Well, 2.8 plus 2.8 is 5.6. So right away, our supply isn't powerful enough. It's not got enough energy, or it hasn't got enough energy to get over my wall that I've just doubled in size. And so therefore our circuit won't work. But we can just give it more energy, right? We can increase the supply of this. We can make it to 10, 20 volts, maybe even 100 volts if we want. If we did 100 volts, then, well, we can string together quite a few LEDs. I mean, this wall will be pretty high, but we're giving it enough energy to get over that wall. So can we do that? In a sense, yes, we can. But there are other effects of that high voltage. There are other components in this circuit that may not be able to handle that high voltage. Let's take a look at some of those. So if we have high voltage here, let's say, argument's sake, we're going to put 100 volts in here. And that high voltage, that 100 volts, is going to meet a couple of components here. Here's one of those components. This is a MOSFET, if you remember, right? And it's going to come in. That 100 volts is going to meet its drain. That's the name of the arm of this MOSFET that goes up here. And between the drain and the source, another name for a terminal of the MOSFET, we might see the full supply voltage. That might be 100 volts going over the drain to source of this MOSFET. Here's another place where we're going to see that 100 volts show up where we may not want it. That 100 volts is going to be between the gate, which is this terminal of the MOSFET, to its source. So the gate to source voltage of this MOSFET could be experiencing 100 volts. Again, it may not be very happy. Here's another component. This is that transistor, that BJT transistor. So that transistor, from its collector, which is this terminal, to its emitter, which is this terminal, it might also see as much as 100 volts, just like this MOSFET over here. And also these MOSFET over here, they're all going to see quite a high voltage. We better make sure that they can handle it before we start sticking that much energy into it. Let's fire up or bring up the data sheets for some of these devices, and that'll help us figure out if these things can handle it. All right, so here's the data sheet for the BJT transistor. So the 2N3904 transistor. If I scroll down here on this data sheet, we'll see it pretty soon. There it is. Right in the first part, it talks about its limiting values. This table here, we do not want to exceed these values. If we do, the transistor is probably not going to function, or it may die an unpleasant death. So here it is. The second line of this table says VCE, so the collector emitter voltage. That's those terminals that go from here to here. The voltage across these parts has to be less than, according to this table, 40 volts. All right, so that means 40 volts is our max. We can't go to 100. We only can go to 40. And even then, we're not leaving any room for error. So we want to be a little bit under 40 realistically or practically to make this thing work. Well, let's take a look at another one of our components. Let's take a look at the MOSFET. So this is the MOSFET. And if I scroll down here, you're also going to find another table that says absolute maximum ratings. This is, again, we don't want to exceed these. And if you look at the very first line, it talks about a drain to source voltage. So if you remember from our schematics, here's the drain and here's the source. The voltage across these two places cannot be more than, according to this data sheet, 60 volts. Well, the previous one limited us to 40, so 60 is plenty. But if we go down a little bit more, there's another reference here saying gate to source voltage, continuous, is no more than 20 volts. So the gate, if you remember, is this terminal here. And if we have a high voltage going from the gate to source, it cannot be more than 20. So actually, that's our limit. We cannot exceed 20 volts. And even then, we have no room for error. So we really need to scale that back a little bit. And rather than going to 20, let's give ourselves a 10% buffer for error. So really, we only have 18 volts that we should be giving this circuit as it is right now. If we want to give it more than that, we're going to have to redesign it and change some of these components. Why don't we stick with 18 to keep things simple? Another reason 18 is nice is because, well, 18 volts is a supply voltage that you can actually buy on the market. You can go online and pick up an 18 volt supply really easily. It's much harder to buy a 20 volt supply. Although you can, they tend to be more expensive. So 18 is something that we can get and is accessible to us. So it's a nice number to use. Let's use 18. All right. So if we're going to use 18 volts to power this, will it work with 18 volts? Well, we're going to have to figure that out. We're going to have to look at all the different various walls that exist in the current path. So we know that we're going to have some walls in our LEDs, right? And as long as our LED wall is less than 18 volts, we should be good. But there's more. There's going to be a voltage drop across this MOSFET over here. So there's a wall here that this has to get through. There's also a wall here across this transistor that the energy has to go through. So we got a couple of different barriers that we need to be able to make sure we can surpass. So in order to help figure that out, I've created a diagram here. And so this diagram, let me bring that up. It's right underneath our circuit. Here we are. Is a budget diagram. I don't like the term budget, but it seemed to fit for what we're trying to do here. So let's roll with it. Okay, so we got a budget here. What I want to do is I have two here. We're going to work on the left one first. Okay, the left one, we're going to try to fill up our budget. We have an 18 volt budget. You can see the numbers that we have here. So we get 18 volts to work with. On the left side of this column, I'm going to track our progress with 3.6 volt LEDs. And on the right side of the column, I'm going to track our progress with 2.8 volt LEDs. Why am I doing this? Well, remember, the LEDs have a range. We don't know where the LED is going to fall. It's going to fall somewhere between 2.8 to 3.6. So we're going to have to track both, and we're going to meet somewhere in between. We just don't know where that is. So we better start to track both. So I'm going to start from the bottom and start filling up our budget and see where we end off. Let's start with the very first item. If I bring my circuit back, the very first thing that we need to put at the bottom of this budget is this one item right here. This base to emitter junction. So that part right there is going to have a little bit of a voltage drop. And we know what that voltage drop is. If you remember from a previous video, we found that voltage drop, we measured it. It was about 0.68 volts. But it varies, right? So what I want to do is I want to look at the data sheet for that transistor. That's this one right here. I brought it right back up. And if I scroll down a little bit, you're going to see that there is actually a little bit further. There it is. So the saturation voltage of the base emitter. So this is the terminal that we're interested in, right? The voltage across this point. It says that the maximum is going to be 950 millivolts. Now, we measured it at 680. And from practice, we know that it very rarely reaches that level, but it could. So that might be the very first thing I want to concern myself with. Let's just round it up to 1 volt. All right, so I'm going to round that up to 1 volt, and I'm going to put that into our budget here. All right, so here's our first line of 1 volt, and it's become unavailable to us, right, because of that transistor. There's another one here as well. If I continue up the path, we're going to see that there's also a voltage drop across this MOSFET from the drain to source. After the LED, it's got to go from the drain to source. And there's a voltage drop across that as well. Well, what is that voltage drop? That voltage drop is a little bit more difficult to figure out. If we go to the datasheet for that for the MOSFET, here it is. It's not as easy. It's not in a table, and that's because it varies so much because of all the other circumstances and the way that it's set up. You actually have to scroll down to where you start seeing these charts. Now, I have to admit something. When I first started looking at these charts, oh my gosh, I was so confused. It is not easy to look at this and try to figure out what you want. It is really complex. It took me a long time. And so as a result, I think I'm going to avoid diving into how I figured out what the voltage drop is going to be. Let me just leave it at this. It was the very first chart here, the figure 1, which compares the drain source voltage to the drain source current. I know the kind of current we want to push through. We want to push through 350 milliamps. If you remember from a previous video, that's the kind of current that our LED, the ones that we're using today, have been designed for. So that's what we want to push through it. So based on that, I was able to look at this chart. And again, if you're interested in the details as to how, let me know. And perhaps on a different video, I'll dive into this, or maybe in the chat, I'll dive into how I did it. Now, again, I'm no expert at this sort of stuff, but I think I was able to figure it out. Anyways, I looked at this, and through this chart, I was able to figure out that the drain source voltage, where did I go? I wrote it down here somewhere. Oh yeah, it's going to be approximately 1.5 volts maximum. All right, 1.5 volts maximum. So if we go back to our budget, I'm going to add another 1.5 volts to this, which is going to bring us up right to about here. All right, so this has also become unavailable to us because of the way I can put this data sheet away for now. So let me put the data sheet away. There we go. Okay, so now we're at, well, this point right here is about 2.5 volts. So that's how much budget we have. And the rest of this is available for us to work with. Okay, so let me start filling this in. I'm going to start from the side over here, and I'm going to need my calculator. I know you can't see my calculator, but I'll tell you the numbers as I'm working my way up. So I'm going to start from 2.5, and I'm going to add in my first 3.6 volt LED. So basically, I'm just going to add 2.5 and 3.6, and we're going to end up at 6.1. So the first place I'm going to end up in is right over here. All right. So this point is our LED 1. Now I want to add another LED. So here we're building up our walls. We're going to add another 3.6 volts. We're at 9.7 now. So 9.7, there's 9.5, 9.7 is probably around here. All right, LED 2. That's 9.7. Let's add another one. 3.6 volts. We're now at 13.3. So there's 13.5. Let's say 13.3 is right here. All right, LED 3. Let's keep going. 3.6. 16.9. All right, so now we're going to be right over here. LED 4. 16.9 volts. Okay, so I can't add another, right? I mean, you can clearly see if I try to add another LED, we're going to exceed our budget, and our 18 volt budget won't be enough. But we have enough for 4 LEDs based on 3.6. Well, we're going to have to do the same for 2.8 as well. LED 4. And as it happens, we should be able to add another one. Yeah, another one brings us to 16.5, which we'll put right here. But I can't. I can't put another LED because remember, the reason I'm tracking both is because we don't know where our LED voltage is going to lie. It's going to lie somewhere in between here. So if I add another one, well, what if our LEDs are closer to 3.6 volts? It's not going to be enough. So actually, I can't add another one. I'm going to have to stop here at 4 because that's what showed up here. So these are where my LEDs are. And if I'm sitting at a 3.6, let's say I'm sitting back on this side at 3.6. If I have that, what's left over here? Well, what's left over here is 1.1 volts. That's what I have left over. And that 1.1 volts, what's happening to it? Well, if I'm giving my system 18 volts, that 1.1 volt is being burnt off as heat. That's what will happen if these LEDs are all lined up. This gets burnt off as heat. And we can calculate how much energy is being burnt off because remember, we're assuming 350 milliamps are going through our circuit. That's lighting up these LEDs. So this excess voltage at 1.1 volts at 350 milliamps, we can actually calculate the power that's being lost or wasted here. And the power is, in this case, I think it's going to be about 385 milliwatts. That's the power that's being wasted with this configuration. But what if our LEDs are at 2.8 volts? Well, we got a lot more here than 1.1 volts. In fact, this one works out to about 4.3 volts. So let's put it over here, 4.3 volts. And at the same current, so 350 milliamps, we actually have a power lost or wasted of, let's see, 1,505 milliwatts. That is a whole lot of power that's wasted as heat, 1,505 milliwatts. Okay. Is that acceptable? Well, we don't know. We can figure out if this is acceptable by bringing back our datasheet. Let me do that right now. So let's bring our datasheet back up. All right, so here's our datasheet, and I think we're looking at the right one. Yeah, so we're still looking at our MOSFET datasheet. So let me scroll up here just to make sure we're looking at the right one. Yes, so this is our BS270 MOSFET. Now I'm going to go back to the absolute maximum ratings again, because remember, this extra voltage or this extra power is being dissipated by our MOSFET. That's where the excess is going. It's going into heat. It's turning it into heat and it's pushing it out through the actual body of the device. And over here, it tells me that the maximum power dissipation of this particular MOSFET is 625 milliwatts. Uh-oh. Based on our calculations, we could be pushing as much as 1,500 milliwatts through this. So what do you think is going to happen? This MOSFET is not going to handle it very well. It'll burn, it'll melt, it'll get destroyed. So this is not going to be a good idea. The only way we can do this is we're going to have to upgrade our equipment a little bit here. So we may have to choose a different MOSFET. As it happens, I've got another one. Okay, so take a look at this. So I'll just go back to our screen here. This is the MOSFET that we've been working with so far. That's the BS270 MOSFET. I happen to have, remember, by the way, we're trying to use components that I got lying around the house, right? Or lying around my workshop. So we do have this one. No. Okay, some of you are going to look at this and go, wow, Arif, you've chosen a really old component. And it is an old component. But like I said, I've got these lying around. I've got one of these. This is a BUZ71A MOSFET. Look at the size difference here. Look how big that one is compared to the one that we're using. Another interesting fact about this is if I flip this over, you probably already know this, but if I flip this over, you'll see that the backside has got a big giant metal plate on the back of this. And it's also got a hole. Well, that giant metal plate is actually used to dissipate power. It's used to dissipate the heat, and when that hole is used so you can anchor this to like a heat sink or something. And so you can actually, this thing will handle a lot more power than one of these little BS270s. How much more power? Let's take a look at the datasheet. So I have the datasheet here for the BUZ71, and let's pop that open and take a look at this. So I'm going to scroll down to where I see my, where is it? Oh, sorry, went too far. Absolute maximum ratings are right here. So the maximum power dissipation of this BUZ71A is 40 watts. 40. That's 40,000 milliwatts. Remember, the BS270 was only, what, 680 milliwatts? This thing will handle it no problem. We're expecting to lose 1,500 milliwatts. This MOSFET, the BUZ71A, without a problem, it'll handle it. Okay, so in terms of power dissipation, it's good. Let's double check the rest of the specifications. The drain to source breakdown voltage is 50 maximum. We're under that, we're at 18. And the gate to source voltage is 20. That's the same as the BS270. So we're also good, thumbs up. So I think we're safe to switch out the BS270 MOSFET with this BUZ71 71 MOSFET. All right, so this is going to put us in a better situation because we can handle that kind of power. Well, not but. And with this new MOSFET, we get to change some of these the energy or the various the VDS, so the voltage across the drain to source of this is going to be different than the one that we saw. So let me bring back the schematic, and you'll see what I'm talking about. So here's the schematic, and if you remember, the original BS270 was this device right over here. This is the one that we're talking about. And I'm changing this to this MOSFET, a bigger MOSFET to handle the power dissipation. So if we put this bigger MOSFET in, well, the voltage from the drain to source, that drop that we're talking about earlier that ate into some of our budget, it's still going to be there, but it's different than the BS270. And as it happens, it's a lot less than the BS270. So if you remember, the BS270 voltage drop was close to 1.5 volts. It was being eaten up just by that MOSFET. So what I want to do here is I want to track the same budget using the BUZ71A. So let's start tracking it here. The first portion here, this little bit here, this was because of that the transistor. So that's still there. We still have a 1 volt being eaten away because of that transistor. So let me make sure we color that in. It's gone. So what is the voltage that the MOSFET is going to eat away? Well, for that, let's take a look at our datasheet. Luckily, we have it open. So here's the datasheet. Now, just like the BS270, the datasheet for this BUZ71, it's really tough to read. In fact, it's even more tough to read. If I scroll down to that chart, the one we're interested in is this one right here. It's even harder to read, A, because the lines are thicker. Whoever printed this datasheet made thicker lines. Also, the ranges are bigger because this datasheet or this MOSFET is capable of handling a lot more current than the old one, than the BS270. So look, the y-axis here goes all the way up to 30 amps because this thing can handle quite a bit, and it's got a lot more lines on it. So I have to admit, it was really tricky for me to look at this and try to figure out what that voltage drop would be. But again, if you're interested in understanding how I did it, let me know. I'll dive into my my estimations, but I eyeballed it, okay? And I eyeballed it using this chart right over here, that the voltage drop across this BUZ71 is going to be about 0.7 or 0.07 volts. That's a lot less than the other one, right? So 0.07 volts. If we look at them together, 0.07 is so small that we might as well just not even include it. So if I go back to my drawing here, my budget drawing, that 0.07 volts will barely make an impact on our budget. It's so tiny. So we might as well just leave it at 1 volt. So now, using the new MOSFET, which I'm going to very strategically place up over here. All right, there we go. I'll put this MOSFET over here. And I'll put the old one over here. So just so we have a reference. Okay. We got a lot more room to work with, which is kind of nice, right? We got a little bit more to work with. So let's do the same thing we did with the BS270, but now we're going to be starting from a little bit lower. So I'm going to make sure, let's get rid of this so we don't really need it anymore. Okay. All right, so we can also look at the power that's being wasted in this situation. It's going to be a little bit more from the previous one, right? So this voltage, extra voltage here is, I think we worked it out to 2.6. So we're at 2.6 volts at 350 milliamps. And the power that's being wasted for this column is, where were we? This is 910 milliwatts. And for this side, it's a bit bigger. This was 5.8 volts at 350 milliamps. Power wasted was 2030 milliwatts. So that's 2 watts of power being sent off as heat. This guy over here is going to get warm. If it's pushing out 2 watts of power, it will get warm. So we really want to make sure that we get rid of that heat effectively. All right, so are we done? Maybe. But there's still quite a lot of energy being wasted. If we left things the way they are and reduced the amount of power that we put into our system, so we went from 18 and we brought it down a little bit, well, if we brought it down, we can actually get rid of that wasted energy. So we can fine tune this by reducing the amount of power that we're giving to our system. But like I said before, when it comes to power supplies, there are some power supplies that are easy to buy and plentiful and others that are not. And I said 18 volts you can get. You certainly can. But if we were to bring this down to, I don't know, 16 volts, which would be nice, that gives us at least 4, we can actually then run 4 LEDs and reduce the amount of wastage. 16 volts is going to be a little bit harder to find. The more common power supply that is available is 12 volts. So if we brought this power supply down to 12 volts, well, that means we can't run 4 LEDs anymore. We can only run 3. So let's entertain this for a moment. Let's bring this down to 12 volts. Everything above here, we're going to ignore. And if we now have 3 LEDs, we now have a tiny bit of excess voltage there that we're using. In this case, it worked out to 0.2 volts at 350 milliamps. That worked out to 70 milliwatts of wasted power. And here is our excess. In this case, it worked out to, where did it go? I wrote it down here a second. There's 2.6 volts at 350 milliamps. The power here wasted worked out to 910 milliwatts. Same as that. So what does this mean? This means if we left our power supply at 18 volts, regardless of which LEDs we purchased, we can run 4 of them, but we'd be wasting somewhere between 910 milliwatts to 2030 milliwatts, guaranteed. If we brought our power supply down to 12 volts, we can only run 3, so it's 1 less LED. We can only run 3 LEDs, but now the power that we're wasting is somewhere between 70 milliwatts and 910 milliwatts. We don't know where, but somewhere in between there. That's a lot less than the power we're wasting in using 18 volts. And quite frankly, it's only 1 LED less, is 3 LEDs, which is still going to be sufficiently bright. So in terms of efficiency, I think it's better to stay with the 12 volt supply. We will be able to use all 3 LEDs, and if we have 3.6, we're actually getting very close to peak efficiency here. Right? This would be, as far as I'm concerned, a better choice. I think I'd like to stick with 12. Just for a side note though, there are LEDs on the market, which are called high efficacy LEDs, where you can actually buy and you'll get a much tighter range. So some of these high efficacy LEDs, you might be able to get them at like between 2.6 to 2.85 volts, which means the range is tighter. And if that range is tighter, then suddenly we don't have so much unknowns. And if we were to use these high efficacy LEDs, we would be able to increase our voltage even more. We can then get the next level up, which would be a 24 volt supply. And off that 24 volt supply, we might be able to run like 7, maybe even 8 LEDs if we were lucky enough. So there are ways to improve this, but we'd have to get into another realm of LEDs. And for now, because we're kind of using stuff that I got lying around the workshop here, why don't we leave it at that? So I think we're going to leave it at this. I think we're going to leave it at 12 volt supply, 3 LEDs, between 2.8 to 3.6 volts, and that should give us a very nice and consistent result. Now, I was hoping, I have to admit, I was hoping to actually put this together. I wanted to replace the MOSFET, take the BS270 out, and put the new 71 or the BUZ71A in, and then maybe take the 3 LED or take the 1 LED out and wire up 3 LEDs. But I think we're way over time. So what I'd like to do instead is wait until the next video. So this one is especially long one, but there was a lot of meat and a lot of details that we went through here. I hope I didn't bore you too much, but this was important to get through because it helps us size our system to a more practical situation or a more practical state. So on the next video, we'll take what we learned today and we're going to put it to work and test it out with 3 LEDs in our circuit. So until then.